Hey, Franco, I'm going to give it my best shot to work through comments. So let's see. As far as independent variables, mass, type of spring, and how far it stretches, that's great. Listed dependent variables, don't need displacement and don't need velocity. The dependent thing we're going to do is measure time, and I'm pretty sure you show that on your lab. Okay. So if I were going to update anything, I'd be working on that. Let's see if it'll give me some color. Good. Okay. Let me keep going on. Brief statement. This is spring type E. That's what you've got 4 different masses. I'd probably like 5, but that's fine. You did times and then your period, your time per cycle. And so you got these values. And then what did you do here? Same thing. Square root of the mass. Okay, so you probably linearized it. And so let's see what this graph is. So first you got your mass versus period. Here's something I need you to think about. We've got 0, 0 shown, and then we've got an intercept. Is this linear? I think you've determined it's not linear, but your graph is showing something linear. If the data is not linear, don't put a line of best fit, or at least explain the line has been put there, it doesn't fit all the data. So right now it's telling me you've got an intercept of like 0.18 for 0 mass. Clearly, if we evaluate it, it would go to 0, 0. So technically, I'd probably want the line of best fit to be eliminated. And I don't even need a curve of best fit shown. I just want the data there. And maybe you insert a 0, 0 into your data, right? Maybe that helps because I'm pretty sure you said that it was a square relationship. Yeah, square root of mass and period, which is great. And wow, look at that. The intercept is virtually like 0, so it's not significant compared to y values. And I would say that is about as linear as you can get it. So provide an equation. So square root the mass, and it made my graph linear. Do you have an equation for that, right? So what I want to do is find a relationship between period, which is t. Let's see if I can write that down. T, right, is proportional to, right? And I can write, fishy, proportional to the square root of that, of mass. Now, we would end up doing an equation is that proportionality symbol really can be replaced with t equals whatever your slope is times square root of mass. Okay, so if you were to find your slope, right, you that's done. You can plug it in there, and that you get that equation. So the result is my period. The period of the oscillation is proportional to the square root of the mass, or more specifically, if I wanted to predict for a mass, say of 500 or 1,000, I'd put the 1,000 grams in there, and then I'd multiply it by my slope, and I should be able to find the period for that. Okay, so that's kind of the point for that. Let me get here. And I was looking for, right? What else was I looking for? It goes way back to first statement as far as independent variables. You've done change of mass, but have you tested the type of spring? And have you tested how far down you've stretched it? So the displacement of the spring. Each one of the, during the lab, you have the ability to change each one. And if you noticed at the bottom of this lab, the K values are listed, and that's the spring stiffness constant. Okay.